Hello, welcome back to my channel Chemistry with Rahul. So till date we have seen very much important part, very much important perspective of this chapter. So now we will be moving towards the next part of this chapter that is very much important, and that is very much useful for the calculation of like electrode potentials. Electrode potential, it is nothing but we like potential difference also we can say that electrode potential we will be talking about over here. Electrode potential, now we are talking about here, that is the electrode potential. So what is electrode potential? Electrode potential means it is related to a power or a capacity, we can say that power or a capacity which is related to two types of electrodes we are familiar with. One is cathode and one is anode. So cathode and anode, cathode, they basically there is a charge separation. Okay, there is basically what? Charge separation. Charge separation we see in this particular thing, we see a charge separation. So due to charge separation only means positive and development of positive and negative charge, due to that only the EMF, that is in any EMF, or we can say this as a potential difference. Potential difference takes place. Potential difference takes place. Potential difference takes place. Yes. So in this concept, like in capacitor also, we take positive and negative part. So to develop a potential in any solution, suppose we have taken example, like suppose we have kept, I'm not connecting over here, I have just uh, placed here, I have just placed a zinc sulfate solution. I have placed a, this is our zinc sulfate solution. Okay, that's we have taken in earlier examples. And here I have taken the electrode. Okay, this is our electrode over here. This is our zinc electrode. This is our zinc electrode. So in this scenario, what exactly happening here? When when electrodes are left in solution, when we can say that when electrodes are left in their respective solutions. So two types of scenarios can be seen. So, and here also I'm taking our one more solution, that is nothing but this is our solution, blue solution, that is nothing but our copper sulfate. Okay, copper sulfate is there, and then we have to deep our electrode over here, that is a copper electrode. This is our copper electrode. This is zinc and this is copper. Now here we have two cells with their particular solution and electrode. So we have just kept this particular solution and rod along with them. We have not connected this particular thing. So in this scenario, what is going to happen? Suppose this is our solution. This is our solution over here. So this solution has some amount of a pressure over here. This solution has some certain amount of a pressure over here. The solution has certain amount of pressure over here, and here the solution is trying to like it is trying to pressurize that particular electrode. So in this case, that zinc over here, it is converting to Zn+2. Okay, automatically it is converting, and here there is a development of negative charges. Okay, there is a development of a negative charge, so that here we can easily confirm from here, like this is our case first. Okay, and this is case 2. So solution pressure and the pressure which is working on this particular electrode is osmotic pressure. These are osmotic pressure. Osmotic pressure for, it is basically for the electrode. It is basically for the electrode, and this this one is for the solution. This one is for the solution we have taken. So if the solution pressure, we can write this case over here. Now in this case, what is happening? Suppose we have a solution pressure is greater than is greater than is greater than osmotic pressure is greater than osmotic pressure. In this case, what is happening over here? Here zinc is getting reduced, means the weight of that particular zinc is decreasing over here. We can see that the uh, ions from the zinc rod is getting deposited. Here it is getting deposited inside this particular solution. So in this case, here our Zn over here is converted. The Zn means this zinc, okay? Zn is converting to Zn plus 2 and 2 electrons are given over here. So Zn, here it is a, basically it is getting reduced over here. So this is our first thing. Second thing, what we are observing, that weight of zinc rod decreasing. Weight of zinc rod is decreasing. And third thing, what we can see here, there is the electrode potential. What is exactly? Now this is our electrode, okay? So the electrode potential, we can refer this as electrode potential. We can term this thing as electrode potential of this particular. It is nothing but here loss of electron is taking place. So we can term this as a oxidation potential. This is our oxidation potential. Like platinum, it is not an inert, it is an active electrode. It is our active electrode. These electrodes are nothing but active electrode. We name them as a, this is our active electrode. We can write over here also active electrode. So this is the terminology that we are seeing over here, that here in case one over, this is happening basically solution pressure. We can see that the solution pressure is greater than the osmotic pressure. So in this case, weight of zinc rod is decreasing over here, and electrode potential is a oxidation potential. This is our active electrode. Now in this case, now in copper sulfate, what is happening over here? The Cu plus 2 ion is getting deposited over a copper ion. So depositing means it is layering on that particular thing. Layering means the size of that particular thing is going to increase into that. So here we can say that the osmotic pressure, here we can say that the osmotic pressure is greater than, here we can say that it is greater than the solution pressure. Solution pressure. Here this one is greater. So what we can write about this, that here this copper plus 2, which is in ionic form, copper plus 2, it takes 2 electron. Okay, it takes 2 electron, it get converted to copper. Okay, and the second thing what we can say, the weight of Cu rod or electrode increasing. We can see that it is increasing over here. And the third thing that is very much important, the electrode potential. The electrode potential, we observe over here the electrode potential. This is very much important part. That is a reduction potential. This is our reduction potential. So the observation, reduction potential, this is also an active electrode. We haven't connected any wire in between these two cells. Even if, like, even after that, they are showing their basic nature. So this is active electrode. So this is about this, like two cases we have seen when we talk about electrode potential over here. So electrode potential have like case 1 and case 2. Case 1 is related to that particular solution pressure. If solution pressure is greater than osmotic pressure, then we get a oxidation potential. And if case 2, osmotic pressure is greater than solution pressure. So this is the thing that we have to keep in mind. So here we can say that this is our reduction half reaction, okay, and this is our oxidation half reaction. Both the reactions are taking place at simultaneous process. So this is oxidation and both the half cells are there. We have drawn, this is a half cell, this is also half cell, we have drawn over here. So in case of when we have to find out the EMF, we have to calculate the EMF, or we say this as a E cell when we connect them. Okay, when we connect them, we are familiar with this particular thing. When we connect both of them, so what we are going to write over here, we would require the oxidation potential also and reduction potential. By combining both of them, we will be able to calculate our E cell. So E cell can be written as, when we combine them, so what we can write over there, the electrode potential of, that is the electrode potential of oxidation potential plus electrode potential of reduction potential. Here reduction, E of reduction potential. So we read this E value of oxidation potential plus E value of reduction potential. Or we can say that oxidation is always takes place at, we know that that is E of anode plus E of cathode. We can also refer this particular thing as like this. So this is our oxidation potential for anode, reduction potential for cathode. This two terminals, or we can mix up this thing also, oxidation potential of anode, okay, or plus reduction potential at cathode. So this could be possible over here. We can say this, like this terminologies, we can write it over here. So suppose we are taking E of oxidation potential could be nothing but minus of, we are just reversing this particular thing, that is our anode, okay. So this can be written as minus of E reduction potential at anode. We can just write this particular thing like this. This will be useful terminology. We are just reversing that part, and we know that when we reverse anything, any values, it is going to be like that, like it will convert to, if it is a plus, it will be converted to minus, and if it is a minus, it will be converted to plus. So we can put this particular value to this here. So this could be written as, like here we get E cell for this particular thing, that will be nothing but reduction potential at cathode, okay, reduction potential of cathode minus E naught, E of reduction potential at anode. So this could be our formula that we can use it over here. Yes, so this is our main formula that we have to keep in mind. This formula can be useful for us. So E cell, it is equal to reduction potential at cathode minus E of reduction potential of anode. So this is very much useful, and this formula, it is exactly given in NCERT book. Okay, it is similar to your NCERT book. So this is what we have seen over here. It is related to a electrode potential we are calculating. So solution pressure and osmotic pressure, there are two terminology that we have to keep in mind. So when we write like which one is getting oxidized, which one is getting reduced, so this particular process that we have seen over here, now we will be moving towards the writing that particular cell. Suppose we have taken, so in case of that particular thing, we have taken electrode, okay, we have taken electrode, and then we have a solution. That particular solution was there, which the concentration of solution we kept C1, and on the other side we are having what? We are having solution, which is solution, which was C2, and that particular electrode we were having. Okay, that particular electrode we were having over here. So in case of zinc, in case of a zinc, we can write over here in zinc electrode. Always remember on this side, we always write the oxidation part. This is our anode over here. And on this side, we always write a cathode part. Okay. So zinc, and zinc is converted to Zn+2 solution. That was our concentration C1, and the cell, then here we got C+2, that is our concentration C2, and the electrode was copper electrode. So this was a solid, this was also solid. This both are in a aqueous state. So this is how, and for this E cell, okay, that is our E cell, that is E naught cell, that is a standard value we get over here. E naught of a cell, that is a standard value for this particular, that is E cell, could be nothing but E cell we can write over here, that is nothing but this is particularly E of reduction potential of cathode, okay, minus E of reduction potential at anode. So this is the thing that we can write it over here for this particular thing. Now we have to calculate the electrode potential. Now we have seen what are the electrode potential, that is reduction potential of cathode and reduction potential of anode. So what we have to do here, now we will be calculating, that is a calculation of electrode potential. We'll be seeing that calculation of electrode potential. That is also a very much important term, calculation of electrode potential. And for calculation of anything, we need a reference. We need a reference. So here we are going to take a reference of a She. She is nothing but, that is our standard hydrogen electrode. This is our standard hydrogen electrode. Okay, this is what we have to see, and this particular reference is given by IUPAC, okay, International Union of Pure and Applied Chemistry. It is given by them, and we have EMF, two type of EMF we have seen, okay, EMF, and it can be calculated either by, like, two things we have to keep in mind: E of oxidation potential and E of reduction potential. That this two thing we have, and E cell can be calculated, that is nothing but E, it is right, E to the right, we can say that right hand side we have seen, on right we always take a reduction potential minus E of left hand side. This two, we have seen two sides, that is a reduction potential. Again, reduction potential is there. So there are two types of electrode potential, basically two types of electrode potential. We have two types of electrode potential. First one is standard and another one is a non-standard. So first we will be seeing standard potential, standard electrode potential, basically standard electrode potential, and on another side we will be having non-standard electrode potential, non-standard electrode potential. We will be talking about these two things simultaneously. So whenever we say standard means it is something which is fixed, which is not going to change. So when we talk about standard, so we take certain standard, that is temperature, we take 298 Kelvin. That is very much important thing. For standard electrode potential, temperature, it is nothing but 298 Kelvin. Pressure over here, it is nothing but 1 atmospheric pressure. We take a pressure as a 1 atmospheric pressure, and alongside, like here we have taken to, and the concentration of this particular thing is 1 molar. So 1 molar, it is nothing but 1 mole per liter, 1 mole per liter over here. That we have to keep in mind. And when we talk about non-standard, so for non-standard, if any of this condition is not satisfying, okay, I'm saying any of this condition, any of condition of standard, any of condition of standard electrode potential is not following, then we can say it will be a non-standard. So it will be nothing but temperature, either it won't be equal to 298 Kelvin, or we can say that pressure will be not equal to 1 atmosphere, okay, or we can say that concentration, it is not equal to 1 molar, or either of 3, okay, either of 3, all 3. So these are the terms that we have to keep in mind while solving this one. Like there are 2 types: calculation of electrode potential on the basis of reference electrode we are taking, that is a C, standard hydrogen electrode, which is given, which is provided by UPSC. And while calculation of electrode potential, so we have 2 parts, that is standard electrode potential and another one is non-standard electrode potential. So before proceeding, we should understand what exactly the C means standard hydrogen electrode. So what is C? We can say that what is SHE? What is SHE? It is nothing but standard hydrogen electrode. We have seen that it is our gaseous electrode of in which hydrogen gas is filled. In that particular thing. So here hydrogen gas is there, and basically if hydrogen gas is there, so the solution we are going to take, okay, the solution, because in zinc, for the zinc rod we have taken zinc sulfate solution, so the solution will be nothing but the acidic solution. For hydrogen we take acidic solution, that is of H plus ion should be there, okay. And here more thing, we can say that temperature we keep as a 298 Kelvin, that it is now the standard hydrogen electrode itself, the name itself has a standard part. So temperature will be 298 Kelvin, pressure it will be equal to 1 atmospheric pressure, and concentration it will be equal to 1 molar concentration, that is 1 mole per liter, 1 mole per liter. Yes. So in this case, let's draw this one over here, how this particular thing looks like. So in a particular cell we take basically a solution of H plus ion, H2SO4 HCl. We can take a HCl solution for this, because H plus ion, 1 H plus ion will be given out of. So here we take this as a HCl, not H2SO4. If we take H2SO4, it will give 2 H plus ion. So we require this as a 1 molar solution. Okay, this will have 1 molar solution, that is a H plus ion concentration. Okay, and in this case, here we take 1 platinum. This is our platinum sheet, and to that particular platinum sheet, we have a filament like this. We have a particular filament, and here opening further, from here we get a hydrogen gas, and here this particular conduction, this is we key for the conduction. Basically this wire is get connected, and here we have a basically our hydrogen gas, which is at 1 atmosphere pressure. Okay, and this is platinum coated. This is our platinum. Platinum we have seen, it is inert in nature. This is platinum coated in nature. So for this particularly, when for this particular cell, like in electrochemical series also, we have seen the concentration of H plus ion. The H plus is always 0.00 volt. Okay, one end it is at fluorine and one end is it is at the lithium. So lithium is minus 3.08 and this is something plus 2.87, and the H plus is at the center, that is 0.00 volt. This is decided by the IUPAC, and the E of SRP, standard reduction potential, the standard reduction potential, it is not, which is equal to minus of standard oxidation potential. We can say that OP and SRP, both the things are there, and it is given by IUPAC, that is 0.00 volt. The standard reduction potential for hydrogen electrode is always 0, that is given by IUPAC. This is simplified thing. We don't need to do anything over here. That is concentration and all the terms. These are the things that we have to keep in mind. For this is given, the standard reduction potential is 0 and standard oxidation potential is always 0 for this standard hydrogen electrode. So this is the assembly that here we have platinum electrode, hydrogen gas is filled from here. This is HCl solution, and to represent this thing, like this is very much important. This question was asked in IIT mains in 2012 somewhere. So this was nothing but platinum. We take this like this: platinum, hydrogen, which is in a gas form, and 1 atm pressure is there that we are using, and here we get H plus ion, which is in aqueous form. Okay, this will be a 1 molar. So this is the one line representation for this hydrogen electrode. So we are talking about here the calculation of electrode potential. So in calculation of electrode potential, we take a reference of standard hydrogen electrode, which is given by IUPAC. And into that particular thing, we have two parts, that is standard electrode potential and non-standard part. And separation of charges we have seen, like oxidation potential and reduction potential. From that particular thing, we get those two things over there. So this is all about today. I hope till here you have studied, understood all the thing. Keep on studying. Bye bye.